Either no one wants to hear about Spark or everyone else is at House Call Pro. Any questions? Okay, so I want to first talk about the basic idea behind Hadoop and Spark. And then we can see why we don't want to deal with Hadoop. And then we can talk about the languages on Spark, and we start talking more details about Spark. So I'm going to start with old technologies. And I want to solve a very simple problem, right? Most books start with, here's how you count words in a text file with Spark or Hadoop, right? So word count. It's sort of the whole world of Spark. So let's say we have you want to read some file, right? And now we want to write a program to count how many times each word appears in that file, right? So maybe it's a complete works of Shakespeare, right? So we want to do the word count, and then we got some other document which might be written by Shakespeare. So they want to compare, see if the word frequencies are the same. So the straightforward way, you might say, okay, what we'll do is I'll create some sort of dictionary, right? And that's called my dictionary count, right? And then we will go through and zero out all the elements, and I'll skip the part where I take the text and I break each string into separate words, right? We can do a split on spaces or whatever you want. And then we can just basically do something like right? And then I go through this loop, and when I'm done, I can look at count the dictionary, and it'll tell me each word, right, and how many times it was shown in the file, right? But now when we go to Hadoop and Spark, our setup is slightly different. We're going to have one machine, the master, that's where we'll start things on. It controls the rest of the cluster. And then we're going to have worker 1, worker 2, etc., right? Now the problem with solving the problem this way is that what will happen is we're going to take this program, we're going to start it on the master, but the master is going to ship it out to all the workers and have the workers do part of it. So the first problem we have is I've got this file. This file now needs to be sent to each of the machines, right? And we don't want to send the entire file to each of the machines, because if we're using Spark, it should be a big file, right? So we want to break those files into pieces and send each piece to the workers. How do we do that? So Hadoop has two parts. One is the Hadoop distributed file system. And so when we write a file on the Hadoop distributed file system, it's going to automatically disperse the file, break into pieces, and send each piece to the machine. And it's done for us. So now, when I say this, right, when I say read text, right, and I run it on these worker machines, they're only getting a piece of the file, not the entire file. Which means then we're going to have a different count on each of the machines, and then we're going to have to write code to grab those counts and bring them back to the master, right? And then we have to merge all those counts together because they counted different parts of the file. And so either we have to continue writing here, or we do a different approach, right? And so Hadoop, the second part is map reduce. The name is misleading because it sounds like it's just map and just reduce, and we'll see in a minute why there should be something in between the map and reduce. So we'll get rid of the straightforward program, and we're going to do it in a slightly different way. The map part, we're going to write a map function, and the input to map is going to be our text. And then what's our function going to do? We want to take each word in the text, and we want to create a tuple. And the tuple is going to have two parts. The first part is the word, and the second part is just it's going to be one. And so this now, let's assume that text now is, let's see, a cat ate a rat on a mat, right? So that's my text, right? So what's going to happen now is, let's assume we've got, there should be 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4. So there's the middle point. So let's assume that we only have got 2 workers, right? So this file now automatically we split into 2 pieces, right? And so this will be on worker 1, worker 2, right? Now in reality, the Hadoop file system, it breaks files down into blocks, right? People done OS, right? You know about file systems, right? They divide files into blocks, and the blocks are usually, how big are blocks, say on Unix? Anybody? What's that? In Hadoop, the default block size is 50 megabytes. Right. So, well, because we're doing big data, right? And why? I mean, if you only have 10 megabytes of data, why are you running it on Hadoop or Spark? I mean, just run it on your laptop, right? It's gonna be a lot easier and faster. So in reality, it wouldn't. I mean, this is like silly. But now, what do we want to do? Well, now what we're going to do is for a word in text, what do we want to do? We want to some output device. We're going to append what? We're going to create a tuple, and it's going to be W and 1. That's it. That's our map. So that means now that this will be worker 1, worker 2. So on worker 1, we're going to get A and 1 and cat and 1 and 8 and 1 and A and 1, right? And in worker 2, it's going to be rat and 1, on 1, A1, and mat 1, right? After running our map. What's our reduce going to be like? Now what we want to do is we want to find, we've got 1, 2, we got 3 tuples that start with A. We want to combine them all together to get A and 3, right? But the problem we have is that 2 A's are on worker 1 and 1 A is on worker 2, right? So in between applying map and reduce, both Hadoop and Spark, what do they call a shuffle? And what they do, by the shuffle, they're going to say, look, we're going to take all these tuples and we're going to put the same tuples on the same machine using some algorithm. So we might say, okay, what we're going to do is we're going to move this up to machine 1, and then we'll move cat down to machine 2, and so then we get rat 1, on 1, cat 1, and mat 1, right? And at the top we're going to get A1, and I guess it'll be A1 again, and then H1, and then A1, right? It means it occurred once. And then we want to combine these 3 tuples of the same key into one tuple, right, with a count 3. Oh, because we just ran this. And the problem is, I mean, there could be 1,000 of them here, 500 here, and they're 2,000, right? They're scattered all over the place. We want to keep it sort of balanced out, right? Now, of course, here's this example. I only have 8 tuples, which is silly. I mean, it just, say you had 100,000 tuples, right? And so then they're going to use some partitioning device to say which tuples go on which machines, and then send. And this happens for you, right? You don't have to worry about this. The other question is there some nice algorithm they use to, the more time you spend doing that, the less time you do other processing. So I think they just make an approximation, and they reduce. we'll get a key and a bunch of values. But to do that, what they're going to do, the next step is a sort or a group by, right? So they're going to group all the A's in one group, and then we have, and these are all separate groups, right? And now we can run our reduce, and we're going to notice that all these tuples start with the same key, and so we're just going to transform this into basically A and then 1, 1, 1. And that's going to be sent to a reduce. And so what reduce will do here is, we're just going to return a new tuple with the same key, and then I'm going to sum up, take the sum of all those values and return this. And so when we're done, what we get is a list of tuples, right? And the first element is a word, and the second element is how many times that word appeared in original text. So far, so good. Now, there's a number of problems that arise that you may not think of at first if you're not used to doing distributed systems. So I said that the Hadoop file system is going to break the file into pieces and send them out to machines, right? The problem is, what happens if one of those machines goes down or hard drive dies, right? And even then, what does it mean for a machine to go down? Well, we think of it as, your computer no longer runs, right? But what happens if the machine gets stalled for some reason, right? It's running some process and it's taking for a while. How long do we wait before we decide that machine is no longer responding, so it's dead? And what do we do, right? So what the Hadoop file system does is, when it breaks your file into pieces, it doesn't send each piece to a single machine. It'll send each piece to several machines. So if that one of those machines goes down, then some other machine or machines has the same copy of the data, and now it can take over the responsibility, or it can fork off another machine, right, to take up the load. Now, when we're talking about Hadoop, this is it. This is all Hadoop does. So when you write an Hadoop program, it's just a series of maps and reduces, map and reduce, map and reduce. You can do it as many times as you want, but that's all you get, map and reduce. Rich, how would you compute the average of a bunch of numbers, right? Doing map and reduce. How would you compute the standard deviation using map and reduce, right? So what Spark does is it gives us more tools besides map and reduce. We have map, we've got reduce, we also have group by and filter, and a number of other operations we can do. So the first thing is that Spark has more functionality than Hadoop. Hadoop is just map and reduce. So normally, more functionality comes with some drawback, right? Well, it turns out that Spark is a lot faster than Hadoop. So now you have more functionality and your system is faster. Well, then we can ask, well, which one's easier to use? Well, it turns out Spark is easier to use. So now it's more functionality, faster, and easier to use, right? So then you can ask, what advantage does Hadoop have over Spark? And I only know of two. One is you've already invested a ton of code in Hadoop and you don't want to rewrite it in Spark. So if you start new projects, that doesn't work, right? The second advantage is when you have a cluster of machines working in Hadoop, and inevitably some of the workers are going to get done before the others, right? They're not all going to finish at the same time. For example, if I had a huge list of words and I did the shuffle and the algorithm to distribute them wasn't good, some workers may get more words, some workers get fewer words, and the worker with fewer words will finish first. In Hadoop, as soon as that worker is done with the job it was given for this Hadoop job, it's now available to be used by another Hadoop job. And Spark, when you run a program and that program utilizes n machines, all those machines, none of them are eligible for another Spark job until that Spark job is done. So resource allocation can be better done in Hadoop, but given that Spark can be up to 100 times faster than Hadoop, you're still probably much better off using Spark than Hadoop. So what Spark people did is say, we need this, and so why? There's no need to reinvent the wheel. Hadoop, these two are two separate segments. So Spark just says, we'll just use Hadoop file system. Now, AWS has their own distributed file system, so Spark can run on top of that. So Spark is able to make use of different distributed file systems, but one of them is Hadoop file system. Any questions before I move on? Right. Let's see. Here's this one. Oh, there we go. Yeah, so Spark was created at Berkeley. There's, Spark officially supports 4 languages: Python, Java, Scala, and R. There are some other languages which can use Spark. Since it runs on the JVM, any language that runs on the JVM, so like Kotlin or Clojure, can also use Spark. It turns out that, well, I'm not going to talk about R. I don't think there's not many people in computer science that use R, but there's only 3 languages which have interactive shell, right? So like Python, you can open up and just start typing and then execute. You can do that with Spark, with Python, and you can do it with Scala, but you cannot do it with Java. So when you want to use Java, you write your program and you compile it and then you run it, right? And if something goes wrong, you go back and edit it and compile it and run it. Whereas it's possible both in Python and Scala to, have an interactive session and try this and try that. And you can run them both in Jupyter notebooks, right? So you can use the same. Yeah, it runs on these platforms. To manage the clusters, there's various ways we can do that. We don't have to worry about that. We'll run Spark. You can run it locally on your machine. I actually got 2 Spark sessions running my machine right now. And so it just uses the various cores on your local machine. And that's typically how you want to develop your program, is to do it locally on a single processor machine, just to make sure it works. And then once it's working, you can then run it on a cluster. Like I said, there's different file systems that we can use. And it's what they call the pseudo-distributed modes, which you use when you run it on your laptop or your home computer. Timeline for development. In 1991, Java was started, came out in 95. Java started picking up steam. In 2001, Scala was started, basically in part reaction to Java. 2002, this program called Nutch was started, and 2004, Google MapReduce paper published. People got really excited about this idea of MapReduce, but it really is map, shuffle, sort, reduce. Scala 1 came out then, F#, so we're starting to see some functional programming. Scala is functional and object-oriented at the same time. 2006, Hadoop becomes a separate project. Scala 2 comes out. More VM machines are coming out in reaction to Java. And in 2009, Spark comes out. So what's happened between here and here, there are two important factors that happened. Number one is that functional programming became, I wouldn't say popular, but it was trendy. People were doing it. It's becoming more common use. And the second thing that happened was that the price of memory just kept on going down and down and down. And as a result, right, by the time Hadoop 1.0 came out, Hadoop, it was started when memory prices are very expensive. So what they did is they assumed you wouldn't have much memory on machines, right? Both Spark and Hadoop were created assuming you're not going to use special purpose hardware. You're just going to go and buy a bunch of Linux machines and network them together. And so they assumed not much memory, so they store everything on disk, not in memory. Spark, it was created much later, And they're like, yeah, I mean, it's clear that memory prices are very, very cheap. So they assumed, yeah, that we can have machines with large sets of memory. And so Spark tries to keep as much as possible memory without running to disk. And that accounts for a lot of the performances between Hadoop and Spark, is that you're not reading and writing from the disk. You're just reading and writing to memory, right? And then Spark came, version 1 came out 2014. Now, so in Hadoop, right? Hadoop was created at the time when Java was king, and anyone doing functional programming is like looked down upon. They sort of hid themselves in a closet for like, and how do you do things in Java? Well, in Java, you create classes and subclasses, right? So how do you create your map function? You subclass a mapper, and then you implement a single function, and that's it, right? So here's your mapper function, and you're getting, here's your text, right? And then I'm converting it to a string instead of whatever text is, and then I'm going to tokenize it in tokens, right? The part I skipped, and then I'm creating, there's this context where we can write, and you're writing a tuple, right? The word and one. And of course, it's Java, so you just can't write one. The output has to be an int writable, so it can write to disk, right? So this is your map function. And now we need a reduce function, right? That's another class that we subclass, and that class has one function, right? It's like, why are you creating classes with one function? It's like, what? But that's the Java way, right? Back in that was the only option you had in Java. You couldn't create standalone functions. And again, here it is. There's a key you get, so the word, and then the values is an iterable. So it's you take all those tuples, right? And you find all the tuples of the same key, and you pass in that key, and you pass in, right, all those values, and there you do, right? You iterate through them, you compute the sum, and then you write out the new key and the sum. But now we need a program. So here is the program. We have to create a configuration, and so we figure the job we want to run, and so we have to tell it output we want, what classes we're going to do for our map and for reduce, various formatting things, and output. And then when we write in our reduce, when we write the output, it's actually going to be written to a file, and that file will be then accessible from the main master machine, right? I don't expect you to follow this, but the key points are you had to write subclass, a mapper function and a reducer function, and then write another program. Here is a complete program in Spark using Python. Now we have to import PySpark stuff to the part session, and then it's assuming you're going to pass in the name of the file as an argument. So this is extra. We need to create a Spark thing. We'll talk about this later. And then we're going to read the file. And once we get the lines, we first called flat map, which what it's doing is it's doing a split. But since lines is a collection, this lambda is going to split each item in the collection into sub-collections, and then flat map takes all the sub-collections and instead of having collections inside collections, it just flattens it all out. So it's one big collection. And then I create my tuple, right? There it is, x and 1. And then I call reduce. And then I write the output to the file. So when I say Spark is easier to use, this is why, right? You don't want to be using Hadoop. And now, whatever machines we used in this process, they're all locked by our Spark job until we say Spark stop. Once we say Spark stop, then our job ends, and all those machines on the cluster are freed up to be used by other Spark jobs. So when you run it on a cluster on AWS, when you're paying for it, you probably don't want to forget to put stop. In Java, it's a little bit more, I mean, it's like, standard Java, right? It's just a little bit more verbose, which makes it a little harder to read. Again, we're, looking for arguments, and then we're building a Spark thing again, except now we know what it is, because in Java we have to specify what type it is. We're reading the file, and then we're using flat map again. It's just a little bit hard, a little more verbose. And, then I'm using map to pairs, and then I'm doing reduce, right? Here's the same program using Scala. But again, we're building a Spark thing. In Scala, we have to declare variables, but there's type inference, so it'll type it for us, so we don't have to say what it is. I read the file, flat map again, reduce by, and then so both Python and Scala I can make it a lot easier to see what's going on than the Java version. Scala, Spark is written in Scala. So the Scala APIs are always going to be up to date, right? Because as soon as you write it, as soon as they add a new library to Spark, it's automatically available in Scala. It's not automatically available in Spark because they have to then write the Spark connection. The one thing you have to be careful of now is when you're writing a program in Scala, everything is on the JVM. When you write a Spark program in Java, everything is running on the JVM, right? Because that's the Java runs on the JVM, and so Spark runs on JVM. Scala runs on JVM, but your Python code does not run on the JVM. It runs on a separate process because it's not a JVM language, right? And that you have to be careful for several reasons. One is if I have data in my Python code and I want Spark to do something with it, it has to get from the Python runtime into the JVM. How do you do that? You serialize it, because you have to send it across a pipe, right, a Unix pipe, and then the JVM has to then read that and then deserialize it, which is going to take time. I mean, this is inter-process communication it's a lot faster than network, right? But it's not as fast as doing the computation directly. Now, they've done a very good job of hiding lots of times you think you're doing Python, but you're not. You're actually doing everything in Spark. But there are times when Scala will be 10 times faster than using Python. And we'll talk about some of those cases later. Now, it turns out if you just want to use Spark using Python, you can install it just in Python, right? And it's pip install PySpark. That's it. And it'll download a bunch of stuff. You know, the standard thing is download, and you watch it for a while, and it downloads a bunch of packages, more packages, and then it's done, and then you're all good to go. Now, if you want to do this and have it available in your Jupyter notebook, then you have to make sure that you're using the Anaconda pip. My machine has several versions of Python, so I have to make sure that when I run pip, I'm using the pip for the version I want to use that package in, right? And then here's a sample program that has no dependencies on files that you can run to see whether or not it's working. So I have to import PySpark. That's the package for PySpark, so you can use Spark. We need this context thing. We'll talk about what that means. I'm defining, it's just a standard Python function, right? And then, okay, this parallelizer is going to map it to different machines. And so the range of zero number samples, what that's doing is creating it's creating 0 to number samples minus 1, right? This is basically a long collection. And then I'm going to call filter on each element of that collection. What does filter do on inside? It just asks whether or not the point is inside the unit circle. It's true or false, right? And then I call count. So I'm counting, and so the filter is going to take that collection, right, of a bunch of numbers, and then it's going to convert them into true or false, right, inside or not. Well, it's only going to return the ones which are inside, and then I count how many there are, and then it turns out you take that count, multiply by 4, and divide by the number of samples, and that's the way I approximate pi. Well, what's the area of a circle? Pi r squared, and the radius is 1. Oh, so it's just pi, right? And so what are we doing is I'm only getting positive numbers, and every time I create a point, I'm seeing whether it's inside here or there, right? So the probability, so if I have enough samples, right, and basically when I ask how many are in there, that's going to be the probability that we're inside the circle, which is going to be proportional to the area of the circle, right? And then I'm only doing one quadrant, so you did multiply by 4 to get the whole thing, right? So the magic is happening here, right? I parallelize this thing, this filter is being done on multiple machines, and the count brings back the answer for us. And so I get count, right? So this is the main program that's going to run on the master machine. And so when I get count back, count is going to bring the answer back from all those machines and combine them. And now this is running on the master machine. I can print it out and I can look at it. This will make more sense later today and next time and next week. There's another way we can install Spark. You go to the Spark website, and there's a download, and here's what the page looks like. And it's what version. The current version is 2.4.0. It's pre-built for Apache Hadoop 2.7 or later. Basically says, well, look, Spark depends on a distributed file system, and so okay, that's the Hadoop file system. That's what this is for. And you download it, and it becomes in a tar file or various versions. You unpack it, and it's all there. You can run PySpark, you can run the Java version, and you can run the Scala and the R version, right? But to run the R version, you have to have R installed, but we don't care. And we download this way, Scala and the Python version, when you run them, you can have an interactive shell. Java, no, you start it up, and then you tell it, run this job. And the job has to, as we saw, you compile it and give it the jar file. Now, it turns out you can install Spark this way and then have this, the PySpark that comes with this, run in Jupyter notebooks. And I'm telling you both ways, in part because it's likely a number going to get stuck, and then you're going to start Googling install Python, PySpark, right? And you're going to page it to tell you how to do it just using PySpark and pip, and there are people out there telling you how to do it this way. So there's two different ways. You don't want to confuse them because they operate slightly differently. But once I install it, I can run PySpark and get all this stuff. And welcome to, if you did this in a fixed width font, it would say Spark. And then you get this prompt, and then you can start typing in code, which isn't necessarily as nice as Jupyter Notebook because you type the code and hit return, and then eventually it goes away. And then if you want to run it again, you have to sort of go find it and put it back. And but if you don't want to install it using pip, then there's various ways of doing. Way to do it is, and this depends upon what shell you're using. For the old people who've got Unix machines, for the Windows people, I don't know how you set environment variables in Windows. The important one is you export the PySpark driver to be Jupyter and PySpark driver Python options to be Notebook. And once you do those, when you go into the command line and type PySpark, after telling your operating system where PySpark is located, it will then actually launch instead of having an interactive shell, it launches a Jupyter notebook for you and connects it to PySpark. Sounds easy, right? I'm sure that a number of you will have problems. So you should expect some frustration. And it's probably better if you start that sooner rather than later. There's nothing like, I have an assignment due in 3 days, and I need to install this, and I just spent 5 hours trying to install the software and it's not working. What do I do? At that point, it's too late to say start earlier. And so basically what I did is I put Spark home, in my environment variables and put this in my path. So now I can just type PySpark and it starts PySpark. I can run the Scala version, I can run the Java version without having to say, slash this, slash this. And actually I did both. I installed it both ways on my machine. They both work. And I actually installed it one way and then I deleted that and the other way, back and forth. So you can do them both. And when you do it this way, it sets up some information for you. So Spark is already defined for you. You don't define it. At some point, you run across this warning message. Using Jupyter Notebook sort of hides it from you. But if you look at, on Unix, when you look at your command window, which you started the Jupyter Notebooks, you'll see this flash by occasionally. And in the past, students have got all panicked about what does that mean and what am I doing wrong? And the answer is, whenever you run Spark on a non-Linux machine, you always get this message, always, every time you run it. End of story. Why? Well, because the Hadoop file system only runs on Linux, right? So it's using your native file system, and so it's looking for, what can I do this? No, I can't do this. So I just have to use Java code to fake it to use your file system. So at some point you may see this, and if you're running in Windows or a non-Linux machine, it's normal. Don't worry about it. If you're running on Linux and you see it, that's not a problem. But now Spark is actually a big system. It's really big. Lots of classes, lots of packages. So I started out with Spark Core. That was the original part. After that, they added Spark SQL. Spark SQL is faster and has more functionality than Spark Core. So most of the time you want to use Spark SQL and not Spark Core. The reason they don't get rid of Spark Core is because Spark SQL is written on top of Spark Core, right? So the big data structure they use in Spark Core is a resilient distributed data set. Distributed because it will, it's run on multiple machines at the same time. Resilient because there's multiple copies of it, so if one machine goes down, right, you're not lost. But the Spark SQL data frame, underneath it is RDD. Now, the reason I call it Spark SQL is because you actually can pretty much do everything in Spark just using SQL. So it'll convert the SQL strings you give it to actual operations on data frames and performance operations as efficiently as if you did it using data frames. And oh yes, a data frame. When you're using Python, we've got Panda data frames and we've got Spark data frames, and they are different. They are different. Now there is a way of converting between the two, but that it requires another package called Apache Arrow. And Apache Arrow is written by the same guy who wrote Pandas. He actually wrote several packages in between. And the Arrow is written to try and be far more memory efficient than Pandas are. But also, you realize that being cross-platform, cross-language was important, so it allows you to convert between different languages. So we'll worry about that much later. And then they added, there's a machine learning library, so it does it. All the things we've talked about so far, machine learning, we can do on Spark. So yeah, that's the original Spark. I'll just call it old Spark just to steer you away from it. And I'll call this new Spark. In computing, we don't like old stuff, right? We like new stuff. So in the core, they've got resilient distributed data sets. They call it an unstructured API because the data RDDs, it's basically tables again, right? But each column doesn't have to have the same, a column does not have to have the same data type. And the data structure itself doesn't keep track of what type of data is in it. What they did with data frames is that now the data frame keeps track of the data types in each column, and since you know what type it is, you can now do more efficient operations because you know what it is, right? And then this is going to drive you nuts. Difference between a data frame and a data set. And so, yeah, I mean, basically, you got your master machine, you put your program on there, and the Spark session, when you do your parallelize and filter and count, the parallelize puts things on the machines, and now your code is being run on the machine, multiple worker machines. And then there's some sort of cluster manager so that when your session says, I want 10 machines, right? You need a cluster manager to give you, here's your 10 machines. When you go to AWS, that's all done. You go, there's a web page and you say, I want this type of machine, I want this many, and then they're talking to the manager for you, so you don't have to worry about it. Typically, when you run it on your own machines, just run local mode. And again, you get this driver process and worker threads that are taking the place of individual workers. The default is when you start up PySpark or the Java version or the Scala version, it checks to see how many cores. Well, it asks the machine how many cores do you have, and whatever it says, that's how many separate workers they're going to create for you. So if you got a 4-core machine, then you got basically 4 workers. You can increase that, but then you're running multiple worker threads on the same core. So there's two things that to keep straight, and it'll take a while to do it. One is a Spark context. If we're doing old Spark, then that's your entry point, right? If you want to do old Spark stuff, you need a Spark context, and that's how you get your RDR, how you read files. That's how you get your RDRs, etc. Right? To do operations on it. That's your starting point. So if you're running PySpark, then PySpark.Spark context gives you your Spark context. Okay, the Spark session is for the new Spark. So if you want to use Spark SQL, you need a Spark session, not a Spark context, and that becomes your entry point. That's how you start things. And it does contain a Spark context to actually do most of the work. But so if you want to do unstructured or RDRs, you need a Spark context. If you want to do Spark SQL, you need a Spark session. And yeah, the two major data structures are, the resilient distributed data sets is a fault tolerant. What does that mean? It means if one machine goes down, we've got a way of recovering. Collection of elements that can be operated in parallel, right? It just means we got this data structure will be distributed across multiple machines in a resilient or fault-tolerant way. Meaning you make multiple copies of the same block and put on different machines. Data sets and data frames. The underlying data structure is an RDD, so you get the same, but it has columns and rows. And you can create SQL tables, then it knows how to read JSON and CVS and all that sort of stuff. Yeah, and RDDs and data sets and data frames are partitioned, and each partition goes on a different machine, and each partition goes on one machine. And how many machines you want to replicate a single partition on is configurable. So at some point you can create a configuration for your Spark job and say, I want each partition to be on 10 machines if you want. You probably don't, but yeah, and resilient distributed means it's on different machines and it's more than one copy. A single partition exists on multiple machines. And the system knows it's smart enough to be able to figure out, okay, that machine is responding very well, so I'm just going to forget that exists and reproduce it on a different machine. So there's two different types of operations, and they do different things, and they act differently. One are transformations. Like map, filter, sample, union, group by. Those are transformations, right? They're done lazily. That is, when you say, do a map or do a filter, it's not done then, right? It's only done when you do an action, right? For example, we saw count, right? That's when the transformations are done. The reason they do it lazily is that typically what you do is you have a series of transformations you're going to do on the same data set, right? I want to map it and reduce it. Well, not reduce, but map and do a filter and then do a group by, right? And if we wait until we actually want the answer, then Spark will look at all the transformations you do and figure out how to do them all as efficiently as possible, as opposed to doing one now and then another later, another later. You can say, okay, we can start building an efficient pipeline to do them all. And this has some subtle performance things you have to be careful of. And that is, I do a map and I get the result and put it in X, and that on the map I do a filter and put it in Y, and then I do a group by and put it in Z, and then I'm done. I go, well, let me do a collect on Z, and let me do a count on Z, right? Thinking that you've already done all those transformations, and every time I do a collect or count or take or first, right, I'm not repeating those transformations. Wrong, right? If you string those transformations together and you assign the result of those transformations to a variable, that variable, they haven't done the transformations yet. It's only when I call reduce or collect on it. So if I call reduce first, I do all the transformations. I call collect on the same variable, it does all the transformations over again. Okay, so what you're referring to, Python has a number of problems, right? And one of the problems is a global interpreter lock, right? And the problem is when you have multiple threads, when a thread needs access to a piece of memory, it can't do it safely until it makes sure that no other threads have access to that memory. And so every time you access a piece of memory, right, it says, oh, I need a lock, which means all threads stop. And then you have to wait until they're all stopped, right? And then you could get the access memory. And when you're done, then all those threads can start, right? So if you're running Python code and you expect to use threads to the performance, forget it, right? It's terrible. I mean, there are ways around it, but just be careful. And all the pandas and NumPy are written in C, and all that C code depends upon the global interpreter lock. So if you're running pandas or any of those libraries, you absolutely need the global interpreter lock. How do we get by with it here? We're not running Python code, right? We're not running Python code, right? When we've got an RDD or a Spark data frame, that's not in the Panda space. It's on the JVM. Yeah. Yeah, otherwise you're just dead. I mean, forget it, right? Yeah, I mean, you look at this API. Now, it turns out another weird thing about Python, I don't quite understand this. When you look at the Java documentation or the Scala documentation, it's like, I'll give you a relatively concise list of the functions, then you click on the function and it expands out. Python documentation in Spark, it's all expanded out. And so it's hard to get a nice overview of all the functions because it's, instead of being 2 lines, there's like 6 lines for each function. And when you got 20 or 30 functions, it's like you're scrolling and scrolling. Where is it? Where is it? And, yeah. So a data frame is a table with rows and columns. It's just like a data frame in Python, except they're not the same data structure. And there's a row, use a Spark version here, but there's a row class that represents each row in a data frame, and they have a schema. And the schema contains the labels of the columns and the type of data in the columns, right? And that's what allows Spark to be more efficient using the data frame than an RDD, because we know these are all going to be numbers, right? And also the partitioner, how do we actually take that data frame and push it out to different machines? And there's a plan, right? So when you do those transformations, it's creating a plan of how to actually execute it. But it's not executed until you do an action, and then it executes its plan. They're different. They are different. So if you read in data as a Panda data frame, you have to convert it to, and it'll be more common to go the other way, right? You've got this monstrous data set. You're going to do a bunch of number crunching on it. And then you want to visualize the results. And so you bring all the thing back to your master machine. And now I want to use Seaborn to visualize it. But Seaborn doesn't know about, Spark data frames. It knows about, Panda data frame. And so you have to convert that Spark data frame into a Python data structure that Seaborn knows about. And it's, in the Java side, you look at the data set, and a data frame is actually a data set with a particular type of row. So a data set, you can define what the rows are. The data frame already has a row class that it uses, but with a data set, you can create your own structure for the row, which we don't need to worry about. Right? That's going to be. So in the Java world, right, you've got that ability to do that, not in the Python world. We have data frames in the Python world, but we don't have separate data sets. So in RDD, again, it's a table, right? But we don't have the information of what types there are. And yeah, there's no compile time, runtime checking, and there's far fewer optimizations. And one example is on a sample data set, the same data set, RDDs consumed 33.3 megabytes. The same data set loaded into a data frame was 7.3 megabytes. So, right, so like I said, RDDs are part of the old Spark. Data frames are a new Spark, and really want to use new Spark. Basically, at one point they claimed that new Spark was 10 to 100 times faster than old Spark. You may want to try downloading PySpark or Spark and making it work this weekend. I will finally have some time starting this weekend, so I'll be doing some grading and creating new assignments. And we'll see people on Tuesday.